Hi, in this video we are going to implement the Bellman Ford algorithm together. So let's get started. I'm going to create a distinct package with Bellman Ford. And we are going to have quite of the same classes as we have seen in Dijkstra's algorithm. We will have a node, we will have an edge, okay. We will have the concrete algorithm, okay, and we will have the app, of course, from which we are going to test our class. So the node and the edge class will be the same as for Dijkstra's algorithm. So it's going to define a constructor with self and name. We will have self.visited is equal to false by default. We will have an adjacency list is equal to an empty list. We will have a predecessor is equal to none, and the minimum distance, which is equal to the sys.max size. I have to import the system, okay. As far as the edge is concerned, I'm going to have a constructor here too, with a weight, with a start vertex and a target vertex. And you just have a weight equal to weight, start vertex is equal to start vertex, target vertex equal to target vertex. Okay, so let's focus on the concrete algorithm, and I'm going to create a class with name algorithm. I'm going to have a static variable has cycle. As you may recall, we have to it's equal to false by default. We can check whether there's a cycle in our graph or not, because unlike Dijkstra's algorithm, here in Bellman Ford, edges can have negative weights. And because we have negative weights, there may be negative cycles, which means that we go from, for example, vertex A to vertex B, B to C, C to A, and we get a negative value for the tour, which means that it is an infinite loop. We keep going around, and it's becoming better and better, because the value of the whole travel, the whole tour, will be less and less because of the negative edge weights. So during implementation it will be clear that I'm going to have a method calculate shortest path. For example, I'm going to have a vertex list, I'm going to have an edge list, and and I have a starting vertex. Okay, start vertex. In the beginning I set the start vertex that min distance is equal to 0. It is where we stand, so we keep going through in range of 0 and the length of the vertex list. And it's very important that Bellman Ford algorithms, we have to subtract 1, because we keep iterating through n-1 times, and later on we make a final loop in order to check the negative cycles. So here we just keep iterating through the edges, and we keep relaxing the whole system in every iteration for every edge. In Dijkstra's algorithm, we keep the relaxation process for only a single edge, but here, in every iteration, we keep relaxing for all of the edges. We keep iterating through this edge, and that's why. So we will have a edge dot start vertex. We have a v equals to edge dot target vertex. We have a new distance, which is equal to min distance plus edge dot weight. Yeah, and if the new distance is the same as for dash cross, this is called the relaxation process. That's we keep checking whether the new distance is smaller than the v that min distance. And if it's true, then the min distance is equal to new distance, and v, the predecessor, is equal to u. It's very important because if we want to trace back, we have a target vertex and want to get the shortest path, we are going to keep backtracking with the help of the predecessors. So it's very important to set the v dot predecessor equal to u. Okay, and after n minus 1 iteration, where n denotes the number of vertices in the vertex list, it is the length minus vertex list minus 1, the final iteration has to be done in order to check whether there's a negative cycle or not. And if self that has cycle for the edge, then just print negative cycle detected or something like that. Okay, and the algorithm that has cycle is equal to true. Okay. Okay, and of course I have to return. I return, and I'm going to have another method that get shortest path 2, and I'm going to specify a target vertex. So I just have to print out that the shortest path to target vertex is equal to the target vertex that min distance. Okay, and we just have to keep backtracking. So we have a target vertex, and while the node is not none, we just have to keep back. We just print out the as okay and node that name. And I think it's not the right syntax. We have to use like this, and the node is equal to the node that predecessor, and that's why we define this predecessor. Okay, I think it's, yeah. Oh, and I have to define the has cycle method. Yeah, if has cycle, then print these out. What's the problem? Okay, and yeah, I'm going to define this dev has cycle, and it's going to get an edge. And here we just have to decide whether after n-1 iteration we have go through all of the nodes. So if we run once more this algorithm and the distance is decreased, it means that there's a negative cycle, because we have found our shortest path. It cannot be decreased unless there's a negative cycle. So we have to check whether the and if edge that start vertex dot min distance plus the edge dot weight is less than the edge dot target vertex. Target vertex dot min distance. I'm not sure whether I have to put something like this, but anyways, it means that return, we return true because it has a cycle, and else we return false, like this. Okay, that algorithm that has cycle, what's the problem? Has cycle equals to true. I think that that's all, and I'm going to from Bellman Ford dot algorithm import algorithm. Okay, and I have made it before the video because it would take a lot of time to do it, so we're just creating nodes. I have to from Bellman Ford that node import node, and of course from Bellman Ford edge import edge. Okay, so here we just creating, what's the problem again? We just sometimes we have to clean the project, and that may help because we have imported the edge, so I'm not sure. We have a target vertex in the edge, we have a weight, start vertex, target vertex. I'm not sure what's the problem. Okay, so sometimes this Eclipse is not being so friendly, but anyways, you just have to save it. So that's the solution. Okay, so I have 4 vertices, 4 nodes. Oh, I'm not too self-consistent. Sometimes I call it nodes, sometimes I call it vertices. It's hard because some professors in Hungary call it definitely node, and the professors of MIT and Princeton call it vertices. So that's why I sometimes call it vertex, sometimes node. But anyways, I think it's not the most important thing to how you name your classes or variables. It's just know that this node or vertex represents the vertices in our graph. I think it's pretty straightforward. So we have A, B, C, D, and we want to get the shortest path. And as you see that there's a backtracking, I mean a back edge from node 1 to 2, 2 to 3, 3 to 4, and we have from 3 to 2 a node. So if we run this algorithm is equal to algorithm, and algorithm that calculate, or what was the name of, or calculate shortest path. What's the problem? Okay. Okay, it's my fault. Algorithm oh yeah, it's a problem. Algorithm okay, calculate shortest path, and I have an algorithm that get shortest path to, for example, node 4. So we want to get to D and calculate shortest path. Yeah, I have to create the vertex list is equal to node 1, node 2, node 3, node 4. I have an edge list. I have to add the edges. Edge 1, edge 2, edge 3, edge 4, edge 5, and I have to give it here vertex list, edge list, and the node 1 is going to be the starting vertex. Okay, so in this situation we should get a shortest path. Shortest path to target vertex is we go directly to D. From A, that's the starting vertex, we get to D. And okay, so yeah, that's all. And I'm going to, yeah, sorry, that's what I was missing. It's so strange because Eclipse doesn't warn me that my predecessor is not spelled correctly, but the solution is not, so it's not going to work the way I want it to work. So predecessor, we can rewrite it with 2s, and the output was fine, but the backtracking was not. So here, if we run this, we get the shortest path, DCBA, and yeah, that's the shortest path because from directly node 1 to node 4, from A to D, it has lots of cost. But if I set it to 0.01, that will be the shortest path definitely. And yeah, the shortest path will be directly from A to D, or DA, whatever. We keep backtracking, we should reverse the list in order to make it more user-friendly, but whatever, we keep backtracking, so from back to the beginning. Okay, and it's very important because I set back it to 300, for example, and if I set it to a negative cycle, which means that it is Bellman Ford algorithm, we can use negative edge weights. In Dash's algorithm, it is not, it is forbidden to use negative edge weights, but here, from node 3 to node 2, I should have negative 10, and let me, in order to avoid infinite loop, we just have to print that if algorithm that has cycle, I mean not algorithm that has cycle, we should print it out that way, because unless we should get a an infinite loop, because it's a negative cycle, it keeps cycling forever. So I think it's not self, it is algorithm that has cycle, because it's a static variable in Python. Okay, so here we should get a negative cycle. Negative cycle detected. It's very important. If you are familiar with stock market rules and the principle of arbitrage, we can use the Bellman Ford algorithm in order to detect these mispricing, for example, in forex currencies, and it is a quite common technique in high frequency trading as far as stock market applications and algorithms are concerned. So I think it's definitely a very good algorithm. It is not as fast as Dijkstra's because we keep relaxing all of the edges in each iteration, while Dijkstra's algorithm we just keep relaxing only a single edge. So it's a very important difference between the two algorithms. But Bellman Ford is much more robust. It can cope with negative edge weights, it can detect negative cycles, so it is definitely worth learning. Thanks for watching.